first thing, I posted up on Slack another extra credit opportunity for you today. This should be an easy one. You should go anyways, even if you weren't getting extra credit for it. But Acuity is on campus today. They're by the stairs of the library from 1 p.m. until 3 p.m. I think is the range. You definitely want to stop by there. Get information about their internship program as well as full-time positions and stuff like that. Over the last several years, our top students graduating from the program have all gone and worked for Acuity. It's up in Sheboygan. It's an insurance company, which sounds boring. Totally not boring. Inside their building up there, if you've ever driven past, they got the giant flag. They have a working Ferris wheel. They have rock climbing walls in this place. I mean, it's like Google. So Acuity is a really cool place, and we'll probably have a couple of students who are working up there come in and give like a presentation. We had a student last year at one of the Grace meetings come and give a presentation for about what he's working on and things like that. But it's a really cool place to work. They do have an internship program during the summer where they pay you and they actually will give you housing up there. So it's definitely go and check it out. I'm presuming that the one of the guys there will be this guy named Jordan, who is one of their recruiters. Mentioned to him that I sent you down and he'll get you onto this list for him and I to discuss you later. I don't know if that's good or bad, but but him and I I go up there, I help them with their recruiting. So every year we go up and I golf with them. We have a pretty good dinner and some, water to drink.
Good. Question. Is it going to be like international student too, or just domestic student?
I mean, certainly for the internship program, international students. For full-time jobs, one thing they don't do is they won't sponsor H-1 visas. But if somebody wants to work there, they don't need an H-1 visa. There's no problem having an international student working there. Yeah. So they're not anti-international students. They're not going to go through the hoops of sponsoring a visa. So typically when you graduate, you're on international students are on OPT for a year. And then since you're in a STEM program, you can get up to 3 years. And then there's, you could sponsor yourself. You can try to get a work visa or something like that.
You can sponsor yourself?
Yeah, it's just money. Yeah, I mean, there's companies out there that will sponsor you and then ask you to pay the dollars. So, then you just transfer your employment to whoever you're working with, but then you'll have the visa. But take most of that with I'm going to give you an 87% certainty on everything I just told you. I don't want to false advertise, but I know quite a bit about it. I work with a lot of international students. I just don't want to tell you like it's gospel. There might be some errors in what I just told you, but I'm pretty confident in what I just told you. Okay, so homework assignment was to do what?
Reading.
Oh, the reading. I already asked that. Okay. So we were doing array stuff last time, right? All right. So let's finish doing the array stuff. Okay, so we started introducing arrays. We had the thing last time where we went through and we separated the Matthew, Mark, Luke, and John by commas, that thing. Mm-hmm. So kind of the idea, the biblical twist on, hey, I have a string, I have to process some data, doing some stuff. So a little bit of Christian worldview mixed in there. But in any case, when we think about an array, remind me, what is an array? If you had to kind of concisely tell me what an array is or define an array, what might you say? Go ahead.
Numbers.
Okay. Okay. I think we're halfway there. So it doesn't have to be numbers, but an array is a collection of like data. So if it were numbers or it were characters, it's kind of like a string in that we index it from bucket 0, bucket 1, bucket 2, so on and so forth. The length of an array is kind of this, gives you back the same kind of value as the length of a string. Let me take that a little bit farther now because there are some differences. So I'm going to do this here. So I'm going to create a string s is equal to hello. And if I want to print out the number of characters in s, how do I get the length of s?
System.child.length.
That's not like F.
Okay, S dot length like that.
You need it. Do you need the S number?
Nope.
Oh, not S.
Yeah, S is the calling string. So since we're calling this guy with an instance of the string class, what kind of method is this?
Instance.
An instance method, since we're calling it with an instance of the string class. How do we know it's a method? The open close parentheses. All right, so we can identify this guy as a method because it has opening closing parentheses. We know it must be an instance method because we're calling it with an instance of a class. All right, and the reason I harped on how do we know that this is a method is when I show you the way we print out the length of an array. It is not a method, it's a field. So an array, so we can say this is an instance of the array class. That's a 75% truth, but just roll with it for a semester. All right, so so this guy is an instance of the array class. We're using that instance to call his length field. So instead of it being a method, it's a field. Both of them boil down to the same kind of value. The length of this string will be 5. The length of this array will be 4. Because we built this array to hold 4 integers. Right? Makes sense? So let me run this real quick. We'll see a 5 and a 4 get printed out. There's our 5 and our 4. Remind me, what does this new keyword do? Real estate agent.
Oh, I'm sorry.
Did I get a selfie? You can take it. You have to take it now.
Okay.
All right, so that's how I photobomb people into places. I don't do it like you know, behind the scenes. I just go right in the front of the picture. Well, they're going to be taking pictures anyways. I don't think they have a whole lot of white people my size in India. When I was in Japan, you get a lot. I mean, they're joking, but you get a lot of Godzilla references. Well, I mean, the average height of Japanese folks is they're shorter than. I guess I don't think so. Not. I would say 5'7" maybe is their average height. I'm guessing, but they're in general they're shorter. I'm more like their sumos. All right. So new keywords like our real estate agent. The job is to go out and get enough land in our computer's memory to hold this many of these dudes. All right. And how big is an int in Java?
4 bytes.
4 bytes, 32 bits, either way. So if we need 4 of those, so we need 16 total bytes. So we're asking this real estate agent to go get us 16 bytes of memory, and it has to be contiguous memory. What does it mean for memory to be contiguous? Right next to each other. Okay. Why does it have to be next to each other?
That's how like the eraser's stored.
That's just how
it makes like when you create a new array, it creates it like it just creates it in like next to each other.
Okay, well, yeah, so it does do that, as we pointed out. Last time we were looking at, I kind of showed you some older C syntax that allows you to do pointer, what's called pointer math. What's a pointer? Yeah, pointer is a variable type capable of holding a memory address. Now, in Java, we don't have a primitive type capable of holding a memory address that we can define. But we certainly have them. We saw this last time. I can just print out AR and see a nice fancy memory address here. So we would say that right off the bat, AR is a variable capable of holding a memory address. That's a pointer. Okay? We just can't explicitly work with memory addresses in Java because they've removed the syntax for us to do that. Okay, we have this asterisks and this ampersand syntax in C and C++ that allows us to directly manipulate memory and do pointer math and things like that. Where Java's removed that and says, look, as your average programmer, yes, it's good for us to understand how things are actually working under the hood, but if you're writing a program and you're going to say, hey, I need to hold 4 integers and I'm going to write a loop that goes through these guys, do you really care where that array lives in memory as long as it works? No. I mean, programming is an applied sport, if you will. And, as long as it works, we're happy with it. But as computer scientists, we're also interested in the theory side of things, right? And this really, what I'm talking about here is kind of a differentiating factor between, if you've seen online these things, you can go and do these like programming boot camps and stuff like that, where you can just do this, 10 hours a day for 3-month thing, and then they guarantee you a job at the end of it as a computer programmer. The difference between that and what you get in college is going to be, you're getting the same programming introduction. For them, you're going to do a whole bunch of real life applications. And here you do less of the real life stuff because they're going to come in more assignment sized chunks. But you're also going to get the theory side here where you understand how things are working under the hood. And now you might say, well, I just told you that doesn't matter. Well, it does matter from a computer scientist perspective, and not just because you can brag about it, but every now and then you'll run into problems where your understanding of how things work under the hood will allow you to come up with a solution, an algorithm for something that somebody who doesn't have that understanding would not be able to come up with, because you understand how things are actually functioning. So I think debugging programs often requires more of that theoretical knowledge than just being able to program under average circumstances or something like that. Okay, so pointer holds a memory address. Why are arrays represented in contiguous memory? Because the way that arrays work is you always go to the base. If I want bucket 3 of an array, so if I say, hey, I want to print out that array at bucket 3, what this is saying is go to the base address where AR lives, so the beginning of that array. Then take 3 steps that are integer-sized steps forward in memory, and then you give me the value that lives there. So it relies on everything being right next to each other, because you always start at the beginning and then take some number of steps in to get to the value you're looking for. If it didn't live next to each other in memory, you wouldn't be able to rely on bucket 3 being 3 steps from the base address. Next semester, when we start looking at some data structure stuff, we're going to be looking at kind of the antithesis of a array called a linked list, where linked lists do not require contiguous memory. And because they don't require contiguous memory, we can't play that game of going to the base address and then just walking 3 steps forwards. Instead, we have to go to the base address, and we have to ask the dude who lives there, where does the next guy in your list live? And then we jump to that memory address. Once we're there, we ask him, where does your next guy live? So each node knows about the next node and where he lives, what his address is. But they're not necessarily all right next to each other in memory. So in general, we would make a comment along the lines of, we talk about arrays, we would say exist in contiguous memory, and related to that are very fast, but also related to that, they are memory inefficient. So in a computer, we have, let's say, 8 gigabytes of RAM in your computer. Let's just say you have a zillion applications open, so you're starting to use up a good amount of your RAM. And you want to create a 1,000 bucket integer array. So you're going to need 4,000 bytes of memory, right? Mm-hmm. And let's just say that you don't actually have any, in order run of 4,000 bytes of memory in your computer available. You might have 4,000 bytes of memory total available, but if it's not right next to each other, you can't use it for an array. Okay, so arrays require one piece of land, if you will, one piece of memory that's big enough to house the entire thing. All right, so if you're starting to represent very, very, very large data sets, you know, billions or something of elements that are large in size, now you're going to start using quite a bit of memory to do that. Yeah.
Are linked lists
Oh, who what?
are linked lists bigger than they export the location?
Well, when you say bigger, do you mean do they take up more memory? On the surface, let's say yes, because each node doesn't just need to know about its value, it also needs to know about its next node, and depending if you're making a doubling linked list, it might also know about the previous guy, so you can go both directions. So it might be bigger, but now on top of that, when you look at how arrays are actually implemented in most of our modern programming languages, they're actually implemented inside of objects as well. So the array itself is probably still always lighter weight because it's just a collection of values that we rely on the given information that everything is some number of steps off the base address. So it's probably a fair statement for you to say that linked lists are more bloated, something like that. But they're more flexible, and we'll talk about this next semester. They're more flexible because as long as we have in our little example there 4,000 bytes of total memory throughout our computer, we can use it. We can store those values because a linked list does not require the data being right next to each other. Okay, but linked list things are not a topic for this class, at least not until sometimes at the very end I start covering it. But right now, just arrays, that's all we care about. All right, so arrays, they must exist in contiguous memory, and that has two things, two related items. One, it makes it fast. I just go to an address and I sprint forward some number of steps and I'm there. So you can calculate the memory address where a bucket lives. Okay, because what's actually happening when you go to get bucket 3 of an array, it's not going to that memory address, then stepping forward 1, then 2, then 3. Instead, what it's doing is it's calculating your destination. It's saying, this is the base address. I'm going to add to that 3 times the size of my steps. Here's my final address. And you can just go there. So arrays are fast because you can calculate the exact address of a specific bucket of an array right from the get-go and just go to that place. But they're memory inefficient because they require the data being held in one fell swoop. And we're going to see some examples of that today. Questions about any of that stuff up to this point? All right. And we understand this example here of strings versus arrays, where technically the way we get the length of a string is through a method, because it has the open closing parentheses on it. The way we get the length of a array is through a field, a variable associated with the array class, but ultimately it gives us the same kind of value. All right, and we don't have to think about the lengths of strings and the lengths of arrays is working differently. An array, if you build an array to be size 4, its length will be 4. The legal buckets are 0 to 3. It's 0 to the length minus 1, just like strings. All right, so they work identically. But now, how do strings and arrays differ? So strings versus arrays. So I'll just have 2 things here, string, arrays. What's a string? Good.
It's an object type. It's a collection of chars.
Collection of chars. Okay, it is an object type, but the important punchline there is it is a collection of char primitive types. That's what a string is. What's an array? Somebody else. Go ahead.
A collection of like type values.
Okay, so this is a collection of like type values. All right. Similar in that they're both collections, but strings are always collections of chars. Unicode based values, where an array can be a collection of any like type value. And once we get a little deeper into arrays, we'll really see arrays can be pretty generic because you can actually store objects inside of an array. And you can just store generic objects. So you can really put anything you want in there that's an object. But don't worry about that for right now. But they have to be like type values inside of an array. So right off the bat, there's a little bit of difference there. All right. There's another big difference with strings. Strings are read-only. That is to say, if we want to change a string, we have to, want to change a character. I'm just going to use a specific example. At bucket 2 in a string, we have to build a brand new string, copying everything over, but replacing what is at bucket 2. So strings are read-only. Once we have them, if we want to change them, we have to construct a brand new string, copying over the parts that we want to keep and changing the parts that we don't want to, that we want to be different. Okay. Where arrays are read-write, we can modify a specific bucket of an array directly without creating a new array. We'll throw one more thing in here. An array is fixed size, and this kind of goes along with that statement about arrays being memory inefficient. Let's say I originally created an array to hold 10 elements, and then I want to put another 5 elements in there. If we think about this like a house, what do? If you have a house and you want to build a sun porch, you just build a sun porch off the back of the house. No harm, no foul. The array version of that is you have a house, but now you want a house with a sun porch. You create a brand new house that's a mimic of your current house, but has a little bit more yard space. Then you build your sunroom in that yard space. And then you go, if you want to be efficient, go back and burn down your old house. Okay, that way you have a new land for somebody else to use. All right, so it's kind of memory inefficient from that perspective. It's inflexible, so it's fixed size. If we want to change the size of an array, we have to build a new array. That makes sense? Now again, this is something that is, if we're thinking about it from what's under the hood, we're thinking about it from a memory footprint perspective, this is not a smart thing to do. We just use the example of a house. That would be a bad idea, right? If a contractor came to your door, you want him to build a sunroom, he says, okay, I got this plot of land down the street. We'll build you a replica house with a sunroom, and then we'll burn this one down. That cool? Probably not what you're looking to pay for, right? Mm-hmm. So in real life, that would never make sense. Now in a computer, we can say, well, it's not an efficient use of memory, but who cares? We got lots of memory. Okay, so maybe in the extreme cases, if you're let's say you're storing patient records for a doctor's office, and at first you have one patient. So you have an array with one bucket in it. Then you get another patient. So you create a new array. You build a new house with one extra room in it. Copy the first patient over, put the next patient in that one, burn down the old house. Now you got 2 patients. Now you get a third patient. Build a new house with an extra room in it. Copy the first 2 patients over, put the third one in there, burn down the old one. Now you got 3 patients. So if you just keep doing that in perpetuity, now it's getting kind of ridiculous, right? What might you do? You might decide I'm going to start off with, I'll just claim enough memory in a row to hold 1,000 patients. Like that should hold me over for a while, right? I'm going to have enough room for 1,000 patients. And, so I have an array that can hold 1,000 patients, but I might only have 3 of them in there right now. So somewhere you're also going to have to keep track of how many patients you actually have, so you know how far you can go into that array to you have where to put your next patient, something like that. All right. So if we want to kind of look at an example like that, Oh, this is very confusing. Why do I do that? All right, so I'm going to dump this stuff here, and I'm going to dump this stuff here. All right, and then what we're going to do is we're going to create a little a scenario here. So I'm going to come up top here. I'm going to say static. I'm going to create a string array so that I have I can call it patient 1, patient 2, patient 3, stuff like that. Okay, so I'm going to create a static string array. We'll call this guy the patients. Okay, and I'll start this guy being equal to a new string array of size. Actually, what I'm going to do is I'm going to make it size 0. Okay. Complete waste of time. So I say, give me a variable that can hold nothing. Give me an array that can hold nothing. All right. So now we're going to write a function here. So it's going to be a static void add patient. This guy will take in a string like patient name that we're going to add to that array. All right, I'm also going to write another function here, static void print patients. And with this guy, that guy's going to take no parameters. And he's going to go through and he's going to print out all the elements in my patient array, all the names of my patients. So it's going to be our stock for loop for int I is equal to 0, I is less than. The name of my patients array is called the patients. Is this guy a class field or an instance field? Class field, how do you know? How do we call class fields? Name of the class. So this would be driver dot the patients dot length. So start I off at 0, keep going as long as I is less than the length of patients, I plus plus, and we'll say system.out.println driver.thepatients at bucket I. That'll print the who? Do we need parentheses in the length? No. Tell me why we don't. We compared strings to arrays a few minutes ago. We talked about the string length method having parentheses because it's a method, and the array length is a field. Go ahead.
I have a question.
Yep.
Can you scroll up by name? So you define the array before name.
Yep.
Do you always do that?
No, I want this guy to be available to all of my different functions here. So I put it up top there. Otherwise, if I would have built it here inside of main, its scope would be local to main. Therefore, if I wanted add patient to have access to it and print patients to have access to it, I would have had to pass it in as a parameter. So this all ultimately comes down to scoping, where we have access to those variables. It was convenient for me to put it up here because I'm going to have multiple methods that all need to have access to the same variable. All right, so print patients here is just going to go through my patients array, printing out the string that lives at each bucket. All right, so now what does add patient do? Add patient is going to take in a patient name. It's going to have to build a brand new array that's one bucket bigger than the old array. Copy everything from the old array into this new array. Then add patient name to the end of the new array. Then set the patient's array equal to the new memory address that we just created. So it now points to a different place in memory. So let's see this work. This is the whole example of building a brand new house with the extension on it, burning down the old house. All right, so what are we going to do? We're going to create a brand new array. So we're going to create a string array. We'll call this guy temp. And he's going to be a new string array that is one larger than our old string array. So this will be a new string array of what size? Driver dot the patient's dot length plus 1. So whatever size the old one was, plus 1. So we have 1 bucket more. All right, then we're going to copy everything from the old array into the new one. Now, how many elements are in the old array?
Length.
Yeah, length. Driver dot the patient's dot length number of elements. And now I have room to hold driver dot the patient's dot length plus 1 elements. So I'm going to copy all of the old elements into the new array. So for int I is equal to 0, I is less than driver dot the patient's dot length, I plus plus. So what am I going to do in this loop? I'm going to put into temp at bucket 0 the value that currently lives in the patients at bucket 0. Put into temp at bucket 1 the value that currently lives in patients at bucket 1, so on and so forth. And after I finish filling up temp, I should have 1 extra empty bucket at the end of temp because I built temp to be 1 bucket bigger. So I'll say temp at bucket I is equal to driver dot the patients at bucket I. So I'm just copying those values over. Then when all is said and done here, I want to set temp equal to the new value that is, I want to set the last element of temp equal to the patient name I just passed in. Where is the last element of temp located? Temp.length minus 1. The length of temp, the number of elements that temp can hold is temp's length. The last legal element is its length minus 1 because it's 0 indexed, right? So we'll say temp at bucket temp.length minus 1 is equal to patient name. Now, when you look at this at a glance, you may say, well, that's kind of weird. I'm using the word temp twice in a row. Again, don't judge a book by its cover. Make sure you resolve what's happening here. What kind of value will that boil down to that I have highlighted there? That's a number. That's going to be an integer. It's going to happen to be the integer that is the length of temp minus 1. So even though I've said the word temp there again, I'm using temp to get its length, and then I'm subtracting 1 from it. That guy right there is going to be a number. This might be the number 5. Okay? So I'm saying I want to set the array temp at a certain bucket equal to something else. What bucket? That number bucket right there. What am I setting equal to? This patient name. All right, now the last thing we're going to do there, and let me show this in a picture here first. So I'm going to come back in here. I'm just going to show our scenario. Yeah, this is fine. All right, and then I need some arrows. So originally, I'm going to assume that the patients, the original new keyword, generated memory address 100 to keep things simple. So the patients points at memory address 100. And then in my add patient function, I create a brand new array temp that can hold 1 more element than the patients, and let's just say that that guy generated memory address 200. So what do I do in there? I go through and I copy, I make temp one bigger. I copy everything from the patients into the equivalent bucket of temp. So bucket 0 from here is equal to bucket 0 from here, so on and so forth. Then in the end, I add my one extra value to temp. So at this point in time, temp actually holds the correct version of my array of patients, correct? The very last thing I want to do then is I want to say driver dot the patients is equal to temp. If I were to print out temp, what kind of value would I get? Go ahead.
Memory address.
Memory address. If I were to print out driver dot the patients, what kind of value would I get? Memory address. So by our picture here, if I were to print out the patients, I would get 100. If I were to print out temp, I would get 200. I wouldn't get the contents of that yet. That only happens when I access the individual buckets of an array. All right, so we good with that? So when I have an array, those guys are pointers. They hold the memory address, which is the base address of that array. So this very last line here where I say I want to assign into the patients the current value of temp. What I'm saying is I now want patients to be equal to the same memory address that temp is equal to. So what does that effectively do? That makes patients point to the same place temp points to. All right, now, is anything pointing here right now? No. So Java has something called automatic garbage collection. All right, and most of our modern languages have automatic garbage collection. And what does this mean? In older languages, like C/C++, when we created new memory using keywords like new, malloc, etc., that kind of thing, allocating memory, we were responsible to give that memory back to the OS using keywords like delete. We were responsible for cleaning up our own messes. If I created an array in C and C++, and then I was done using that guy, I abandoned that memory, it was my responsibility to delete that, to say, operating system, I'm no longer using that. You can now assign it to somebody else next time they try to allocate some memory. Okay? Now, if you didn't do it, it didn't mean that your program necessarily crashed. But what you would have is you would limit the amount of memory your operating system can hand out, because you still have this place up here, let's say reserved, even though you're not using it anymore. You didn't hand it back to the OS. Now, with automatic garbage collection, we have a situation where let's say memory that has what's called a pointer count that has reduced to 0 is automatically handed back to the OS. And what do we mean by pointer count? Pointer count is the number of variables that point at a memory address. So in our picture here, this guy up here used to have a pointer count of 1. Now he has a pointer count of 0 because I changed the patients to point to a different place. So this guy has a pointer count of 0. So now you can think about it like Java has this garbage truck that comes by, notices nothing points to this guy. He's an abandoned chunk of memory, and Java will automatically give it back to the operating system. That's automatic garbage collection. All right. So as programmers in modern languages like Java or Swift, things like that, it is not our responsibility to clean up our own messes. Having said that, what's the side effect? What's the downside of that? If we don't clean up our own messes, somebody else has to clean them up, right? And that takes time.
Yes, it does.
So to have this automatic garbage collection running, to have this dump truck coming and picking up after us, means that we are taking some performance away from our programs by allowing this guy to go and clean stuff up for us. Okay? In some languages, you have the option whether or not to use automatic garbage collection or not. Java is one of them. You can, if you use the command line arguments, you can turn off automatic garbage collection in Java if you want to write kind of a server-side script or something that you want to be very, very, very fast, and then you decide I'm going to be responsible for deleting my memory. But generalistically, as a modern programmer, you probably are not going to be in the habit of creating new memory and then deleting that memory. That doesn't mean that you shouldn't be aware of it, because certainly as you start writing software for, let's call it, lesser and lesser machines. If we're on a big computer with it's plugged into the wall, lots of hard drive space, lots of RAM, lots of processing power, we maybe worry about that less than maybe you're writing software for a smartwatch that's operating off a battery, has less onboard memory, has less all these other things. Maybe now all of a sudden we think about, maybe we don't want to give up that performance for garbage collection. Then you get even smaller when you start getting into like the Internet of Things, where you have, your toaster has a little microchip thing on it and things like that. It has very limited amount of memory, and we have to be very careful about how much memory we actually use. At that point in time, you might want to have direct control over memory and not rely on automatic garbage collection, which is going to take up more of your memory just to exist, to be there. All right. And what we've seen, actually, if you want a kind of a practical example of this, when iPhone programming first started 10 years ago, it was 12 years ago now, I guess, right? No, 11 years ago. 11, because the first year you didn't have the App Store. So 11 years ago, what you had is you used a language called Objective-C, which is an older programming language that does actually have automatic garbage collection built into the language. The language supports it. But by default, when you were writing an iOS app, the automatic garbage collection was disabled because you were working with a relatively slow computer compared to a desktop computer, and they decided it's going to be in performance's best interest to have the programmer clean up their own messes and not rely on this extra program running around through memory cleaning up. Now, when you program an iOS app, it's when we were still using Objective-C to write iOS apps, eventually it did get to when they turned on our automatic garbage collection by default. Now with Swift, it's just on. In fact, I don't know for sure that you can turn it off with Swift, but if I were guessing, I'm guessing you probably can turn it off, just because you might be in a scenario where that might make sense. But in general, it's automatically on, because the things that they assume you're writing Swift for, Apple Watch, Mac App Store, as not that many people write for that, or iPhone, these are all devices that Apple has decided, well, we have enough CPU power, we have enough memory on these things that it's not that big of a deal. All right, but certainly something that we want to consider and we want to appreciate about Java, that Java is cleaning up after us, cleaning up after our own messes. And that can be a little bit dangerous as a modern developer, because we're not used to having to clean up our mess for ourselves. So if you learn to program in a language like C or C++, where you were always having to allocate memory and then deallocate that memory later on, and now you get to Java, you're like happy, like, oh my gosh, this is so much easier. It's nice that it does it for me. But if you never knew that old scenario, and you just assume all programming languages clean up after you, now you're kind of a danger to yourself, because when you start, dabbling in, future Internet of Things type stuff, where you're writing programs for little tiny microcontrollers, and you don't necessarily know that it's disabled our automatic garbage collection, you now don't have the context to know that, oh, I have to clean up my own mess, because you're used to just always having done it, never having to do it. Kind of makes some sense. At the end of the day, is it probably going to be a big deal? Probably 99% of the time, nobody would notice. You're just wasting a little bit of memory. And chances are you'll reboot your computer before you've run out of system memory. Okay, but these are effectively things like memory leaks. Okay, in computer programs, when we have memory that was abandoned that can no longer be used by anybody because it's still flagged by the operating system as being memory that's reserved. Some of our modern operating systems will, well, most of our modern operating systems now will actually cover our back by when a program closes. So when your C program has stopped running, it'll go and release all the memory that C program requested because it's no longer on the books. Yeah.
Oh yeah, I was going to ask. So that when you like force close a program on a computer, it does automatically free that up.
In a modern OS. So definitely in the last couple versions of Mac OS X, and certainly in Windows 10, probably it goes back to XP, would be my guess. It may even go back further. I mean, I don't want to promise you that, but certainly in our newest OSs, this is something it does. Yeah, and that has to do with when you take an operating systems class, one of the things you'll talk about in there is this idea of a microkernel. So our modern day operating systems are much more modular. So you have different parts talking to each other. So what will end up happening is inside the microkernel, you'll have this subcomponent that's your memory manager. And you'll also have a subcomponent that's your process manager. And that's the dude who's running, in this example, your C program. So when that dies, he will tell the memory manager that all the memory that guy was dealing with is no longer needed because this program has died. And then that memory manager will do his little job. Before, when you had a monolithic approach to operating systems where you didn't have this microkernel, where you had the whole operating system just written as this giant blob, you were reliant on the programmer who wrote the OS or the group of programmers to make sure that that this guy, the memory management component, happened to notice that another program stopped because these guys weren't talking to each other. They weren't separate modules. Just kind of modern operating system stuff. Again, not a topic in this class. Topic for, what's that, 350? It's the OS class. Okay, but again, an example of how, grand ideas of computer science, all these things are related to each other. You just look at it through different lenses in different classes. Does that make sense? All right, so in any case, in our last little thing here, we said we're going to set the patients equal to temp. So we updated the value that the patients held to be equal to the same value that temp points to. Abandoning this, allowing Java garbage collection to clean up our mess, no big deal. This function will then end. What will we do? We will bounce back here to, well, I haven't even called it yet, but I'm going to come in here to main, and I'm going to add a bunch of patients. So I'm going to say for int I is equal to 0. I is less than, let's just do 10 patients for right now so it doesn't scroll off the screen too much. All right, so I'm going to create 10 patients. And then what I'm going to do is I'm going to call driver.addPatient. And we're going to call each patient patient followed by a space concatenated with the current value of I. So it'll be patient 0, patient 1, patient 2, so on and so forth. All right, so I'm going to add my little function here to call my function here to print out, to add those patients. Now I want to create something that will print my patients. So here's this other function down here, print patients, and this guy goes through and just prints out each patient that's in there. And maybe beforehand we do a little system.out.println, put a little asterisk, patient list, make it look all official like, right? Okay, and then maybe at the end there we do, at the end here we do system.out.println, and then just, beautiful. All right, so just kind of so we can visually see where our patient list stops and starts. All right, so after I add my patients up here, I'll go ahead and say driver.print patients. And when we run this, we see that we have our 10 patients that get printed out. Now, from our perspective, like, oh, that just worked. Everything was fine. No problem. Okay. But what we didn't notice is all the new memory we were creating along the way. So we're gonna throw that in so we can kind of see what's happening. So every single time we call add patient, I'm gonna print out a little line here. I'm gonna say system.out.println. I'm gonna say the patients. I'm going to concatenate onto that driver.the patients. Then I'll concatenate onto that a space, then temp : concatenate onto that the value of temp. So what we're going to do is we're going to ultimately see the value of the patients changing over and over and over again. Seeing it move to new places in memory. All right, so this was the original patients. Then it was this different memory address, which was the memory address of temp here. You see how these two match each other? Then it was this memory address, so on and so forth. So in the end, the final memory address of the patients was 47089E5F, which happened to be the last, actually, the real last value of the patients would have been the last value of temp, which is 4141D797, because ultimately that was guy was finally handed off. I'm printing it up at the top of add patients. But punchline for us is we're seeing that we are indeed building brand new houses, copying everything over, and then abandoning the old house, letting automatic garbage collection clean it up. That makes sense? So we're being horribly memory inefficient here. And this is just with 10 patients. Okay? If I pump this up to 100,000 patients,
Oh my.
now we're actually seeing something pretty interesting here. So that felt like it was pretty slow, right? It took some time for it to run. I'm going to do something here. It's just going to be a little different.
Was it just that the screen couldn't keep up without that?
No. So I'm just going to come in and instead of calling add patient, I'm going to say system.out.println. I'll just print out some. I'll just bang on the keyboard. Just going to print some stuff out. All right. That ran a lot faster, right?
Yeah.
Okay. So in here, I'm printing some stuff out.
Mm-hmm.
In here, I'm creating new memory. I'm printing one thing out. And then I am filling something up. If I just remove printing that one thing out here, and I go back to this line, what are we waiting on right now? We're waiting on creation of new memory and the copying of data over from one memory location to another. Time. So we think of creating an array as being free. Fine, we're using up more memory, but who cares? We have plenty of memory. Well, now we just saw time play a factor in here. The first time we had a 1 bucket array, then a 2 bucket array, then a 3 bucket array, all the way up to a 100,000 bucket array. But each time through, we had to create brand new memory, copy everything over. So now we're starting to feel our operating system working. Okay, the new keyword is requesting brand new memory from the operating system, who's saying, here's this new place for you that can hold your 630 strings that you've asked for. So then you go and say, okay, great. Now I'm going to copy all that stuff over, and then I'm going to go and put that last thing in. And I'm going to return. Then we're going to do this all over again. So we're relying on our operating system to go and search through memory, finding a new place that's big enough to hold what we want to hold. So now we're feeling our computer work. Does that make some sense? Mm-hmm. All right. But now something I want to show you here is when I ran this, it was an instant when I just was printing stuff out. I'm printing out 100,000 things. It was a lot faster than what we just ran into, but it was an instant, right? Mm-hmm. Took some time. So one of the other things you'll learn about in the operating system class is something called context switching. And context switching is when one program leaves the CPU and another program comes onto the CPU. Every single time we print something to the screen, that requires us to talk to the input-output system of the operating system, which means we no longer have instructions for the CPU to work on. Now it's the operating system that has to go and print out the stuff that you've asked it to print out. So remember when we looked at the Hello World program in assembly? What did we do? We loaded 4 registers up with some values, and then we interrupted the CPU and said, okay, you've done everything you can. Now we're going to ask the I/O system of the computer to go and, we're going to say, go and do your job and print something out. And it's going to display it on the screen. Then your program goes and gets back into line for the CPU, comes in, it then goes and it loads up the registers again for the next value you're going to print. Then it leaves the CPU. Then we ask the I/O thing to go and do it again. So we're feeling that movement of going onto the CPU and leaving the CPU, doing I/O, getting back into line, getting onto the CPU, leaving the CPU, going and doing I/O and get back in line, so on and so forth. Context switching is really expensive. Again, time. Usually when we use our computers, we don't feel time because computers are so fast. Does that make sense? But now we're feeling time. So even though this was a lot faster than the creating memory thing, we still feel this as time. Whereas if I didn't print this out here and instead just did one final print at the end, which is printing out 0 patients, but it's still going to try to print nothing, we see that our program runs instantly. I'm printing out 2 things. We feel less time because it is less time because I/O is expensive. And one of the things you might see, one way you might see this type of thing in our modern day IDEs like Eclipse or Android Studio or something like this, is it's kind of common when you're writing code to maybe print stuff out to the screen, just so you can kind of like, oh, I want to see what the value is here, I want to see what the value is here. And they encourage you, rather than using system.outs like this, to use the built-in debug thing that will write something to a console. And if you always use the debug command to write something out, then there's usually a button when you go to compile or build your program for the final version to disable debugging. And that will ignore all of your debug lines. So when you're writing it, you'll see all your output and stuff like that. But we've just proven that writing stuff to the screen is expensive. Certainly don't want that in our finished product. That's a testing thing, right? Mm-hmm. So by always using the correct debug stuff, and we'll look at this when we get over to the when we start doing Android stuff. We can use, instead of system.out.println, we can use the debug tools or the log tools. And then we can turn that off when we go to actually build it to release it onto the store, that type of thing. Make some sense? Mm-hmm. All right. So again, these are things that computer programmers might not necessarily learn if they weren't understanding the theory side of things as well. Or they would learn it and not necessarily know why. It's like, oh, just do it as a debug and then turn off debugging later because that's the way you're supposed to do it. Something like that, not knowing that under the hood punchline. Mm-hmm. All right, so back to this. We saw that this guy is clearly expensive. So even if we weren't printing out in here, we've said printing is expensive, right? But even if we're not printing out in here, if I'm having to create 100,000 new arrays and copy stuff over, that took time. Measurable time, okay? You know, not the 1 or 2 seconds. This is, you know, what are we coming up on, 10 seconds or something like that? But it'll, huh?
Enough to notice.
Enough, yeah, definitely enough to notice. Definitely enough to notice. All right, and there we have our final thing. But we knew along the way that we created a whole bunch of new memory. A whole bunch of new memory. Extremely memory inefficient. But we have the garbage collector that went through and cleaned it up for us, right? No harm, no foul. Who cares? But we don't care. Okay. Well, what could we have done differently here? Well, maybe I could have said, maybe we come up here and we say static int max patients, and we decide we want to have up to 100,000 patients. Something like that. And then we have a static int current number of patients. And that guy starts off at 0. I don't have any patients yet. Let me shrink this down. So now I'm going to move my this patients line down 2 lines because I'm going to build it in terms of the max patients. So instead of setting it at 0, I'm going to say I'm going to initially build my array for the maximum number of patients I think I will need. So now we can, we could have just put 100,000 in here if we wanted to, but in this case we're saying, look, you set your max patients variable here, and whatever you have here, then any place you need that value for the maximum number of patients, you can just use that variable. It's more of a choice. Otherwise, you can just remember it's always 100,000. But if you need to use it in 5 or 6 places, rather than writing 100,000 or remembering that it was 100,000 in 5 or 6 places, you can just always use the variable max patients, which always holds your 100,000. All right, so I create this array to be big enough. Now when we come down and we add a patient, I'm going to create a second add patient. Static void add patient 2. This guy will take in our patient name. So rather than creating a brand new array here, I'm just going to add the new patient at the correct place and then increment the number of patients I have. So I will say driver dot the patients at bucket driver dot current number of patients. So originally that would be 0. So the first patient I'll put at bucket 0. This guy will equal patient name. And then I'll say driver dot current number of patients plus plus. Now, technically, I could have said the plus plus in here if I wanted to, because we understand how plus plus works. If it comes before, it comes after, but nobody's impressed if you do that and get the right answer. Much easier to read. You say, look, that's what I want to do there. Then I want to increment. Make sense? So what am I going to do to add a patient? I'm going to put the new patient in the correct position in my patients array. Then I'll increment my current number of patients by 1. That's how adding patients will work. Now, when we print patients, rather than printing up to the length of our patients array, which in this case would be 100,000, I might not have 100,000 patients in there. So instead, I'm going to print out to driver dot current number of patients. Show me all the patients I actually have, not all the buckets that are in my array where I'm going to have a whole bunch of gibberish or empty spots in the array. That makes sense? Mm-hmm. All right. So now if I use add patient 2, we remember how complex add patient was, or time consuming add patient was. If we use add patient 2, we're done. Same final output, right?
Mm-hmm.
But happened way faster, didn't it? Orders of magnitude faster. Because we didn't create new memory each time. Instead, we created memory once and just decided, look, I'm going to build the giant stadium. One day, maybe we'll fill it. Does that make sense? So we can say that's not cost effective, right? In real life, so like you take some small college team and you build them a 50,000 spectator football stadium or something like that. So, like we had 8 people at our game on Wednesday. Yeah, but maybe one day. Maybe one day. Okay. So we're going to remember that we currently only have 8 spectators, but we're gonna have enough seats for whatever, just in case, right? So that's what we're doing here. We're kind of being memory inefficient, less memory inefficient than we were being before, just because of how big our numbers got. We were always adding, creating brand new memory. But now we are at least being time efficient. Make sense?
Mm-hmm.
Questions, comments, concerns, bribes? All right. I will put up a homework assignment. I don't have time to give it to you right now. It won't be too bad. For Tuesday, that I'll be creating some lectures for you to watch and some reading assignments and assignments for your next several classes. Remember, I leave for India tonight, so we won't have class next Tuesday, next Thursday, the Tuesday after that, or the Thursday after that. I come back on October 11th. But you will have lectures for every class. You won't have to show up here, but you'll be expected to watch the YouTube lecture, do the homework. I will be available via text and via Slack and all that stuff. Remember, I'm 10 and a half hours ahead, so if I reply at weird times, just deal with it. There's a difference. Okay. I will try to put up the lectures as early as possible rather than waiting to the day of that class. That's my intention. I don't want to make promises, but that's my intention. That way, if you want to work ahead, you can. All right? All right. I will see everybody when I get back, but please do ask questions if you need to. I will have full internet access and all that jazz. And I'll paste this code up on Slack right now, too. I'll put the homework up here in like a couple of hours. It'll be a homework assignment related to what we just did, not too difficult, just to practice with arrays.
That makes sense. You probably need
Could be in the